We've already looked at structural isomers, but let's just review what we have there. When you have two molecules that have the same molecular formula, but they're connected differently, they're called structural isomers or constitutional isomers. So if I look at butane here, you can see it's 4 carbons, 10 hydrogens. What about this compound? Well, this is 2-methylpropane. 4 carbons, 10 hydrogens. They are structural isomers. What about these two compounds? If I look at them, you might automatically think they are structural isomers, but they aren't. They are just flopped around. One's flopped around with respect to the other. This right here has 4 carbons and 10 hydrogens, and so does this. But if I go to name it, 4 carbons, butane. Longest chain here goes like this, 4 carbons, butane. So they have the same name, so they are not structural isomers. They're what we call conformational isomers. Or another thing that we will call them is just identical. They're not different compounds, but just different arrangements of the compound in space, rotating around. So how do you distinguish between structural isomers and conformational isomers? There's a little decision tree that will help you here. Do the molecules have the same formula? If they have different numbers of carbons or hydrogens or any other atom, they are not isomers. We will say they're unrelated or not isomers. If they do have the same formula, then how do you identify if they have the same structure or not? If they have the same structure, they will have the same name if you're using the system that I've taught you. Conformational isomers have the same name. Structural isomers will not have the same name. So you look for structural isomers with different names. Sometimes you can just see it with your eyes before naming it, but to double check, you can name it. So now I want you to try this. Can you classify these as either structural or conformational isomers? Well, if I look at this, you can see that these all have 5 carbons and 12 hydrogens. This is 5 carbons, 12 hydrogens. Now let me name it. Okay, this is going to be pentane, and the methyl is on the 2, so it's 2-methylpentane. This is pentane, but the methyl is on the 3. They have different names, so they're structural isomers. What about these two? If I look at this, they are both C5H12. If I look at the name of this, this would be 2-methylpentane. If I look at this, you might have named it 4-methylpentane, but that name would be wrong. Remember, you always have to go from the end that gives you the lowest number. So this is 2-methylpentane, and this also is 2-methylpentane. They're both the same thing. So we say they are conformational isomers, or we will say they are identical. What about these? You can't name these, but you can see the difference. If you look at this, this is a ketone. First check the formula, and you would see it's C3H6O3. C3H6O3. Then if you go here, you see you've got a ketone functional group, a carbonyl with a carbon on either side. Here you have an aldehyde functional group, a hydrogen on one side and a carbon chain on the other. They can't be the same. They have different functional groups. So these are structural isomers. Another type of isomer that we have are something called cis-trans stereoisomers. Whenever you have two molecules that have the same connectivity, but they can't fit inside each other, we call them stereoisomers. Cis-trans isomers have to do with sides of the molecule. Let's look down here at this compound. This is 1,2-dimethylpentane. If you notice, this actually has an up position shown right up here, and this has a down position shown right here. They're on opposite sides of the plane of the ring. But if I look at this one, you can see they're both down. Both down. They're on the same side of the plane of the ring. Because they're up and down on one and down down on the other, they won't fit inside each other. They are non-superimposable. You would have to break a bond to make them each other. So they are stereoisomers, and they are a type of stereoisomer that we call cis-trans isomers. Stereoisomers can't fit inside each other, and they have the same connectivity. You know, look around the ring. Carbon, hydrogen attached. Carbon, hydrogen attached. A 5-membered ring. Same connectivity. It's just the sides of the ring that the methyls are on are different here and the same here. Cis is for the two that are on the same side. Trans is for the two that are on opposite sides. I remember this for cis, together like sisters, and trans just, it means, in so many words, you know it means across. So these are cis-trans isomers, which we also say are a type of stereoisomer. You can have cis-trans isomers on a ring if there are two groups, two substituents on that ring. You can also have cis-trans isomers with alkenes. When I look at a double bond, it's very rigid and doesn't allow for rotation of the molecule, so you can't draw the sides flopped around and have them be the same. It's like two people holding hands. You can't twist. You make one of them do cartwheels without breaking the grip between the two hands. So the double bond does not allow rotation here like a single bond does. So when you have them together on the same side versus opposite sides, then we have cis-trans isomers. So to find a cis isomer, what you do is you look for two carbons in the double bond, and their groups are on the same side. So they have to be on different carbons in the double bond. Two different carbons, opposite side, those are trans. If you're having trouble seeing it, draw a line along the line of the double bond and circle the substituents. If two groups are on the same side or two groups opposite, then what you have are cis and trans isomers. There's a third type of isomer, and that is something called enantiomers. This comes from chiral carbons. You find this a lot in biological molecules. For instance, carvone from spearmint looks identical to carvone from caraway seed, but this tastes like spearmint and this tastes like caraway seed. They have a different taste, and the reason is that you've got a chiral carbon right here, and you can see they look like mirror images, but they don't fit inside each other. If I look at this carvone, this group over here with the double bond and the methyl is up. If I flip it over in space, so I grab the left-hand side and pull it over to the right, making it flip over, then that group over here is down now. This is the same thing as this. But if I make the mirror image, you can see this is up. And if I were to flip it over, it would then be down. I wouldn't be able to fit this inside of this, because this flipped over would make it down when the ketone is pointing over here to the left. That's what makes a different flavor. This all comes from this carbon right here, which we call chiral. And we call carvone from spearmint and carvone from caraway enantiomers. Enantiomers are non-superimposable mirror images. It all comes from chiral carbons. Chiral means handed. So go ahead and put your hands in front of your face and look at them, and you can see that they are mirror images except for maybe a ring or a scar that you might have on your hand. If in your, this was visually, if you were to take your right hand and try it, insert it into your left hand, you would find that the palm would be on the wrong side and it would just be wrong. Okay, those are non-superimposable. When do we have chirality in chemistry? It's when an atom has 4 different groups. When it has 4 different groups, it's going to have a non-superimposable mirror image, and we call it a chiral atom. So here are 2 atoms that have 4 different groups, 4 different colors on them. And you can see this is a mirror image of that. See, this is going back and that's coming out. Okay, now what I'm going to do is I'm going to try and superimpose this on this one. So I turn it around in space, and when I turn it around and I bring it over here, you can see that the red and the black are switched, but the pink and the yellow are in the same place. You can't superimpose them. Enantiomers are non-superimposable mirror images, and they come from a chiral carbon that has 4 different groups.